Hi, I'm Tove Larsen. I'm a group leader at ERVAG, the Swiss Federal Institute of Aquatic Science and Technology. I'm also an adjunct professor at the Technical University of Denmark. I will share with you my experience working on a WASH project for urban slums in the Global South. I hope you can use some of my experience for your work in the Arctic. And who knows, perhaps one day the Arctic may profit from mass-produced WASH technologies originally developed for the huge markets of the Global South. There are many differences between the cold Arctic, with plenty of space, and the warm, densely populated Global South. But one thing is common to all human beings. We all depend on personal hygiene, and we all want privacy and dignity when we go to the toilet. About 15 years ago, a new actor entered the WASH sector. Bill and Melinda Gates realized how many children under 5 would die every day from poor sanitation. So Bill Gates started to talk about toilets. He was the first one who was able to attract huge public attention to a not very fashionable global problem. A little more than a decade ago, the Bill and Melinda Gates Foundation launched the Reinvent the Toilet Challenge. They drew attention to the fact that so many people had no access to dignified sanitation, and illustrated in a very simple way the health effects of the lack of safe sanitation and hygienic water supply. Bill Gates had a dream. He dreamed of a safe recycling toilet that would cost only 5 cents per person and day. It would recover energy from feces, nutrients from excreta, and even drinking water. The Bill and Melinda Gates Foundation invited scientists from all over the world to think about this problem and to come up with a toilet which could deliver all this. The Gates Foundation was in a rush. If you wanted to join the program, you had 6 weeks to come up with a proposal, and if the proposal was successful, roughly a year and $100,000 to provide a proof of concept for your technology. ERVAG was invited to participate, and I was the one who took up the challenge. I asked 3 colleagues with different backgrounds to join me setting up the project. They are all experts in their fields. Harald on the design of toilets, Christoph on sanitation in the Global South, and Eberhard on the processing of wastewater. This is how the team looked when we finally could start the project. Diversity was key, not only for the proposal, but especially for our work together during the very intense year we had for our proof of concept. We were quite cautious and did not want to promise too much. We did not believe that after just 1 year, we could come up with a proof of concept for the toilet Bill Gates really wanted. Our proposal was a little more down to earth. We focused on developing a shared toilet, probably a squatting toilet, which would work with 3 separated streams: undiluted urine, dry feces, and 1 stream of water which would be used for hand washing, anal cleansing, and cleaning some parts of the toilets. We suggested container-based sanitation for excreta and on-site treatment for water to be recycled within the toilet. We would work mainly on the toilet and a little bit on the transport. Resource recovery from feces and urine at the scale of 1,000 people, as intended in this project, would need some work, but it's not really a big challenge. The ERVAG engineers, including myself, therefore concentrated on developing on-site water recovery at the scale of 10 people. We were not really sure that this could be done, but we thought that we had a good chance. The reason was a new technology which had just been developed. Marina Peters, a PhD student at ERVAG, had suggested using gravity-driven membrane filtration for the production of drinking water from surface water in poor households of the global south. At the time, nobody really thought it would work. Marina used ultrafiltration, which is an excellent method to produce drinking water, but in large plants with high pressure, not just with gravity. And we all expected that the filter would clog. It is common knowledge that such filters need frequent backwashing, and this is difficult to do in a household. But we were all wrong, and Marina could show that it worked. The water flow was not as fast as in a conventional setting, but it was fast enough and stable. She and colleagues could also show why. With the low pressure, plenty of small organisms would live on the biofilm, and if you ran the filter correctly, without overloading it, the membrane would always stay partially open. To solve the problem of adapting the GDM filtration to the toilet wastewater, which would be much more polluted than surface water, we took the advice of the Gates Foundation, and we asked all our colleagues in the engineering department to help us think about this problem. They formed small groups and finally came up with 3 different technical solutions which we could test. The main problem was the contamination with feces when the water was used for anal cleansing. For surface water treatment, we would mainly filter out algae and dirt. In the toilet, we would filter out smelly and pathogenic feces. We tested different solutions, with and without filtration and with and without aeration. We were extremely lucky. Aeration alone was by far the simple solution, and it worked just as well as the more complex pre-filtration systems. So we ended up with a system which was very close to the model GDM filtration, just with some simple aeration and a tap for removal of well-stabilized sludge. We expected that we would have to remove sludge about every 2 weeks, but to our surprise, we realized that we did not have to remove sludge at all, at least not during the year we ran the treatment reactor in the lab. This made the treatment so much easier to manage in the field. In the lab, we ran the experiments with water polluted with a certain amount of feces, urine, soap, and calf blood. Remember, we collected urine and feces below the toilet, and only traces would enter the water stream. Still, the water was quite polluted because we tried to make people use as little water as possible. The water was treated biologically and with ultrafiltration in the same reactor. This is a principle of a membrane bioreactor, or an MBR, which you may know from conventional wastewater treatment. After this treatment, most of the pathogens had been removed, but the water was still not quite clear, and pathogens could regrow. We decided to polish with electrolysis, producing chlorine from chloride provided by traces of urine entering the washwater. This resulted in nice and clear water with some residual chlorine to keep it safe. We could also have used chlorine directly. While the engineers were working on the on-site water treatment, our non-engineering colleagues in the team worked on setting up a co-creation workshop in Kampala, the capital of Uganda. The designers constructed a mock-up of the toilet, and the experts on sanitation in the Global South set up a co-creation event in collaboration with our local contacts, who in the meantime had become part of the project team. The mock-up was assembled together with local craftsmen to get an idea of the tools and skills available. In a workshop, we presented the basic idea of the water recovery. We discussed with the participants whether they would be willing to reuse the treated water after it had been used, not only for hand washing, but also for anal cleansing. This is a difficult question to answer before you are really in the situation, but we had the feeling that people would believe in the treatment technology if we made it work nicely. A vote on the type of toilet convinced the designers that people really wanted a squatting toilet if they had to share it with their neighbors. We walked around in the slum and talked to people, trying to figure out what they would want. And of course, we, and especially the designers, learned a lot about the local conditions. We also discussed the logistic concept, following a methodology which at that time was in development at Ervag. Finally, we decided on the color of the blue toilet. It had to be the right blue color. The one originally chosen proved to be the color of a political party. We came back from Kampala, inspired and motivated to finalize our blue toilet. Now began the integration of the water treatment in the wall of the toilet. Based on our preliminary lab results, we used Monte Carlo simulation to figure out how big the treatment reactor and the clean water tank should be. Harald used this information for his design. There were plenty other details to deal with, like the placement and the number of membranes, which we had to buy off the shelf in a size which were available. It looks simple when it has been done, but normally engineers prefer to optimize the technology in the lab before they involve the designers. In this case, we worked hand in hand, and this saved us a lot of time. This was time which we desperately needed in order to ship the final product to Seattle for the fair in August 2012. We managed, and we were proud of showing our product to the Gates Foundation and to the visitors of the fair. Bill Gates was, of course, the main guest of honor at this event. We did not have the time to make our model really work, but it was enough for proof of concept. There were many technical details, like the button that one should step on in order to open the lid, here demonstrated by the head of the Gates team, Dr. Dulai Cohn. I don't want to discuss all the technical details. Many of them proved unpractical in the field. But let's see what happens when we pull the handle for assessing the excreta containers. When you pull this handle, the feces container self-seals, and you can open the toilet and remove the container without looking at the feces and with minimal hygienic risks. If you unscrew the yellow cap, you can pump out urine. At the Seattle Fair, we got a prize for the nicest toilet and funding for phase 2, where we could build a first working model and test it in the field. We again went to Kampala, this time with a functioning toilet, which we tested at the Makerere University and in a slum area. We found many flaws of the toilet, but people were generally positive towards it. A main flaw was the water quality, which was not as good as we had seen in the lab. We probably had more feces in the water than we expected. We could solve this problem with additional polishing of the water with activated carbon. After a few trials with a column that clogged, we realized that just pouring granulated activated carbon into the clean water tank worked perfectly. We changed nearly everything else too. Replaced the foot pump with small electrical pumps because people thought that children and old people would not be able to use the foot pump. We made the toilet smaller and reversed the position of the treatment reactor and the clean water tank. Generally, this revised toilet was less fancy, but much more robust in the field. In 2014, we tested it in a large urban slum in Nairobi, this time with fewer problems. People really liked the toilet, especially that they had water available for hand washing and personal hygiene, and this time the water quality was good. They also liked the flush, although only the front part could be flushed. One problem remained. We invented a valve beneath the front part in order to be able to separate water and urine. This was a weakness because the otherwise robust valve was clogged with mud when it was raining. We believed in a container-based solution, which we had developed, and we argued that at this scale, one could rapidly get something on the ground. We showed that transport would be feasible and cheap in the densely populated slums, and that treatment and resource recovery at the scale of 1,000 persons could be rapidly developed. The Gates Foundation did not believe us. So colleagues from Earmark took over to develop the toilet further towards full on-site treatment of excreta. Our designer Harald Gründel stayed in the project, got his own grant, and used the opportunity to solve the problem of separating urine and water without a valve in urine separating toilets. He developed the urine trap based on the so-called teapot effect. When you pour a cup of tea or a glass of red wine, and you don't pour with enough energy, you will end with tea or red wine on the tablecloth. This effect has now been integrated in a urine-separating flush toilet produced and available on the market from the Swiss company Laufen. At present, Harald Gründel is working with different organizations to develop low-cost, dry and poor flush urine-separating toilets to use in low-income countries, while we are waiting for the dream of Bill Gates to come true. Another result of the project is a water wall, which is in the process of being further developed by a company for hand washing in schools and similar institutions in the global south. Perhaps this technology could also be useful in the Arctic. You will find information on the different reinvented toilets on YouTube. I have heard that they will soon be presented to an expert panel, but this is all I know. It remains exciting to see whether at some time in the future we will have one of those magic toilets available on the market.